Light travels at 299,792,458 meters per second. Not approximately, not roughly. Exactly that number, precise to the last digit. It is the fastest thing in the known universe, the absolute ceiling of speed, as defined by the laws of physics themselves. A beam of light can circle the entire Earth 7.5 times in a single second. It can reach the Moon in just 1.3 seconds. It crosses the gap between Earth and the Sun in 8 minutes and 20 seconds. In 1 hour, it travels more than 1 billion kilometers. In a single year, it covers 9.46 trillion kilometers, a distance so large that it required its own unit of measurement. We call it the light year. At that speed, you might reasonably assume that light can go anywhere, that given enough time, a photon launched from one edge of the cosmos could eventually reach the other side. You might assume that the universe, however enormous it may be, is at least traversable by the fastest thing that nature permits. You would be wrong. The universe is not merely large, it is large in a way that breaks the meaning of the word entirely. The observable universe alone, just the part we can detect, stretches 93 billion light-years from one end to the other. That means even if you could somehow travel at the speed of light, with no acceleration phase, no slowing down, just pure photon speed from the very first instant of your journey, it would take you 93 billion years to cross it. But the universe is only about 13.8 billion years old. So even light, traveling since the very beginning of time, since the first fraction of a second after the Big Bang itself, has not had enough time to cross the cosmos. It has not even come close. It has covered less than 1/6 of the diameter. Light, the fastest entity permitted by the fundamental structure of reality, the swiftest messenger in the entire cosmos, is too slow. And it gets stranger. The universe is not standing still while light races through it. Space itself is expanding. Every second of every day, the distance between distant galaxies grows. Not because those galaxies are flying through space like shrapnel from an explosion, but because the very fabric of space between them is stretching. The farther apart two objects are, the faster that space expands between them. And at a certain distance from us, roughly 14.5 billion light-years in terms of proper distance, space is expanding so quickly that it pulls apart faster than light can cross it. Beyond that threshold, known as the cosmic event horizon, light will never reach us. Not eventually, not with patience, not with better instruments or more advanced technology. Never. The expansion wins. It wins permanently and absolutely. This means there are galaxies shining right now, at this very moment, stars burning right now, possibly civilizations thinking and building and dreaming right now, whose light will never reach Earth. Not in 1 billion years, not in 1 trillion, not in any conceivable amount of time. The photons they emit are running a race they are physically incapable of winning. They are swimming against a current that grows stronger with every passing moment, and the portion of the universe slipping beyond our reach is not static, it is growing. Every single day, more of the cosmos disappears behind that expanding horizon. Galaxies that our descendants might have one day visited are being carried away by the relentless stretching of space, fading from possibility, slipping into permanent inaccessibility. We are not just unable to reach the whole universe, we are actively losing access to it, piece by piece, galaxy by galaxy, photon by photon, second by second. This is not a distant future problem. It is happening now. It has been happening since the moment the expansion began to accelerate several billion years ago. The universe is drawing a curtain around itself. That curtain is made of expanding space, and it is growing faster than anything in nature can outrun. Consider for a moment the sheer oddity of this situation. We live on a planet where the fastest thing we encounter in daily life might be a bullet, traveling at perhaps 1,000 meters per second. The speed of light is 300,000 times faster than that bullet. It is 900,000 times faster than the speed of sound. It is fast enough to cross the Atlantic Ocean in less than 1/60th of a second. It is, by any standard of human experience, unimaginably swift. And yet the universe has grown so large that this unimaginable swiftness is not enough. The cosmos has expanded beyond the reach of its own speed limit. The light that the universe itself created, the light that travels at the maximum speed the universe allows, cannot keep up with the growth of the universe that contains it. There is something almost paradoxical about this, a kind of cosmic irony. The universe is too big for its own fastest messenger. By the end of tonight, you are going to understand why the speed of light, the ultimate speed limit of nature, the fastest velocity that the laws of physics permit any object or signal to achieve, is not fast enough. You are going to understand what it means for space itself to expand, why distant galaxies are receding from us faster than light, and why this does not violate Einstein's theories. You are going to understand the concept of the cosmic event horizon, the invisible boundary beyond which no signal, no spacecraft, no beam of light, no message of any kind can ever travel. And you are going to confront a truth that most people never consider. The universe is not just bigger than we can visit, it is bigger than we can ever know. There are parts of it that are permanently and irrevocably beyond the reach of any observation, any instrument, any intelligence, regardless of how advanced that intelligence might become. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why light speed fails, we first need to understand what light speed actually is. And to understand that, we need to go back to the moment when humanity first realized that light even had a speed at all. For most of human history, people assumed light was instantaneous. When you opened a door into a dark room and held up a candle, the room filled with light immediately. There was no visible delay, no wave front sweeping across the walls. Philosophers from Aristotle onward generally believed that light moved infinitely fast. It was simply there, everywhere, the moment its source appeared. This assumption persisted, largely unchallenged, for over 2,000 years. Galileo attempted to test it in the early 1600s, sending assistants to hilltops with lanterns, trying to measure the time between uncovering one lantern and seeing the flash from the other. He concluded only that light was extraordinarily fast, too fast for his method to detect any delay across a few kilometers of Tuscan countryside. The first serious crack appeared in 1676, when a Danish astronomer named Ole Rømer was studying the moons of Jupiter at the Royal Observatory in Paris. Specifically, he was tracking Io, one of Jupiter's 4 large Galilean moons, as it passed behind the planet and reappeared on the other side. These eclipses happened with a regular rhythm, and Rømer was attempting to use them as a cosmic clock, but he noticed something peculiar. The timing of Io's eclipses shifted depending on the position of Earth in its own orbit around the Sunday. When Earth was closer to Jupiter, the eclipses seemed to happen slightly early. When Earth was farther away, orbiting on the far side of the Sun from Jupiter, they seemed to happen slightly late. The total variation was about 22 minutes across the full cycle. Rømer realized what was causing this discrepancy. The light from Io's eclipses had to travel across the gap between Jupiter and Earth. When Earth was on the near side of its orbit, that gap was shorter and the light arrived sooner. When Earth was on the far side, the gap was longer and the light took more time to arrive. The eclipses were not actually early or late, they were happening on schedule. But the light carrying the news of those eclipses was taking a measurable amount of time to cross the intervening space. Light had a finite speed. Rømer's estimate, based on the best available measurements of planetary distances in the 17th century, came to roughly 220,000 kilometers per second. The true value, which we now know with extraordinary precision, is 299,792.458 kilometers per second. Rømer was off by about 27%, a remarkable achievement considering the tools available to him. The conceptual breakthrough was enormous. Light was not instantaneous. It had a speed. And if it had a speed, then it also had limitations. It took time to get from one place to another. and if the places were far enough apart, that time could become significant. Over the next 2 centuries, the measurement of light speed was refined again and again by experimenters of increasing ingenuity. In 1849, the French physicist Hippolyte Fizeau designed an elegant experiment using a rapidly rotating toothed wheel. A beam of light was sent through a gap between 2 teeth of the wheel, traveled to a mirror 8.6 kilometers away, reflected back, and returned to the wheel. If the wheel was turning at the right speed, the returning light would be blocked by the next tooth. By calculating the rotation speed at which this blocking occurred, Fizeau could determine the time the light had taken to make the round trip. His result was approximately 315,000 kilometers per second, closer to the modern value than Romer's estimate. In 1862, Léon Foucault, famous for his pendulum demonstration of the Earth's rotation, improved on the method using rotating mirrors instead of toothed wheels. His result was about 298,000 kilometers per second, strikingly close to today's accepted number. By the late 19th and early 20th centuries, the American physicist Albert Michelson, working with rotating octagonal mirrors over long baselines in the mountains of Southern California, pushed the precision even further. His measurements, conducted over decades with obsessive dedication, pinned the speed of light down to within a fraction of a percent of the modern value. In 1905, a young patent clerk in Bern, Switzerland, published a paper that would change the meaning of light speed entirely. Albert Einstein's special theory of relativity did not merely treat the speed of light as a measured quantity, it elevated it to a fundamental constant of nature. In Einstein's framework, the speed of light was not just fast, it was the cosmic speed limit. Nothing with mass could ever reach it. Nothing without mass could ever exceed it. The speed of light was woven into the fabric of reality itself, connecting space and time in a geometry that had never been imagined before. One of the most profound consequences of Einstein's theory was the equivalence of mass and energy, expressed in the famous equation E equals mc squared. The c in that equation is the speed of light. Its enormous value meant that even a tiny amount of mass contained a staggering amount of energy. A single kilogram of matter, if fully converted to energy, would release the equivalent of about 21.5 megatons of TNT. The speed of light was not just a measurement of how fast photons moved. It was a conversion factor between mass and energy, a number baked into the deepest structure of physics. Einstein's theory also revealed that the speed of light functions as a cosmic speed limit because of how it interacts with mass. As any object with mass accelerates toward the speed of light, its relativistic mass increases. The energy required to accelerate it further grows without bound. To accelerate even a single kilogram to 99% of the speed of light would require approximately 5.7 times 10 to the 16th joules of energy. That is roughly equivalent to the energy released by 1,000,000 tons of TNT, and that is only for a single kilogram. To accelerate a spacecraft of any reasonable size to near light speed would require energy reserves far exceeding the total annual energy consumption of human civilization. The energy required to reach 99.99% of light speed would be roughly 70 times larger still, and even that achievement would leave you permanently below the barrier. You would never reach it. You would never cross it. The mathematics forbids it. Absolutely. This energetic barrier is not merely a practical challenge. It is a fundamental feature of the relationship between space, time, and energy. The speed of light is not just a number that happens to be large. It is the speed at which causality propagates. It is the rate at which one event can influence another. It is the speed of the universe's own internal communication system, and nothing, no matter how much energy is applied, can exceed it. In 1983, the international scientific community took the final step. They redefined the meter itself in terms of the speed of light. 1 meter was defined as the distance light travels in 1/799,458 of a second. The speed of light was no longer a measurement. It was a definition, an axiom of the measurement system itself. It could no longer change. because the unit of length was defined by it. But knowing the speed of light is only the beginning of our story. What matters for our purposes is what that speed means when placed against the staggering size of the cosmos. And to understand that, we need to talk about scale in ways that push the limits of human comprehension. Consider this. Light travels at roughly 300,000 kilometers per second. In 1 year, that adds up to about 9.46 trillion kilometers. We call that distance 1 light year, and it is the standard unit for measuring cosmic distances. But 9.46 trillion kilometers is already a number beyond human experience. Nobody has ever traveled 9.46 trillion kilometers. Nobody has ever seen a ruler that long. To make it tangible, consider that the fastest spacecraft humanity has ever built, the Parker Solar Probe, reached a top speed of about 635,000 kilometers per hour during its close passes by the Sunday. At that speed, the fastest any human-made object has ever traveled, it would take approximately 6,700 years to cover a single light year. That is longer than all of recorded human civilization. And that is the distance to nowhere in particular. The nearest star to our Sun is still more than 4 light-years away. Alpha Centauri, the closest star system, is 4.24 light-years from Earth. That is about 40 trillion kilometers. If you could drive a car at highway speed, 100 kilometers per hour, non-stop, day and night, without ever slowing down, it would take you roughly 45 million years to get there. If you walked at a brisk pace, about 5 kilometers per hour, the journey would take 900 million years. You would need to walk for nearly 1 billion years to reach the nearest star. And Alpha Centauri is our next-door neighbor. It is the closest destination in a galaxy of hundreds of billions of stars. Now, scale up again. Our galaxy, the Milky Way, is a barred spiral galaxy containing somewhere between 100 billion and 400 billion stars. The exact number is uncertain because many stars are hidden behind clouds of gas and dust. The disk of the galaxy stretches roughly 100,000 light-years in diameter. That is the distance light would travel in 100,000 years, moving at 300,000 kilometers per second, non-stop, for 1,000 centuries. If you launched a beam of light from one edge of the Milky Way and aimed it at the other edge, that beam would arrive 100,000 years later. During those 100,000 years, entire species could evolve, flourish, and go extinct. Human civilization, all of it, from the first cave paintings to the latest space telescope, spans roughly 50,000 years of cultural development and perhaps 300,000 years of anatomical modernity. The galaxy is so large that light needs longer to cross it than our species has existed. To make this more vivid, imagine shrinking the Milky Way down to the size of a dinner plate, about 25 centimeters across. At that scale, the entire solar system, everything from the Sun to the outermost reaches of the Oort cloud, would be smaller than a single grain of sand, a speck barely visible to the naked eye, sitting about 2/3 of the way out from the center of the plate. And our closest neighboring large galaxy, the Andromeda galaxy, would be another dinner plate, roughly 65 centimeters away. 2 plates on a table, separated by about the length of a human forearm. That is the scale of intergalactic distance within our local neighborhood. Even when you shrink a galaxy down to something you can hold in your hand, the gaps between galaxies remain enormous. But galaxies are not the largest structures in the universe. Galaxies cluster together under the influence of gravity, forming galaxy groups and galaxy clusters. Our Milky Way belongs to a small collection called the Local Group, which contains about 80 galaxies spread across roughly 10 million light-years of space. The Local Group, in turn, is part of a much larger structure called the Virgo supercluster, which contains about 100 galaxy groups and clusters spanning roughly 110 million light-years. And even the Virgo supercluster is just one lobe of a still larger structure called the Laniakea supercluster, which was identified in 2014 by a team led by the astronomer Brent Tully. Laniakea contains about 100,000 galaxies and stretches roughly 500 million light-years across. These numbers are becoming truly dizzying, but we are still talking about structures that are tiny compared to the observable universe as a whole. The observable universe, meaning the sphere of space from which light has had time to reach us since the Big Bang, has a radius of approximately 46.5 billion light-years. The full diameter is about 93 billion light-years. This sphere contains an estimated 2 trillion galaxies. Each galaxy contains anywhere from a few hundred million to several hundred billion stars. The total number of stars in the observable universe is estimated to be around 200 sextillion, that is a 2, followed by 23 zeros. It is a number so large that it exceeds the estimated number of grains of sand on every beach on every continent on Earth. Let us sit with that comparison for a moment. Imagine visiting every beach on the planet, every stretch of coast, every tropical island, every rocky shore, every vast desert whose sand was once a seabed. Gather every grain of sand from all of those places. The total number of grains of sand on Earth is estimated at roughly 7.5 times 10 to the 18th power, or about 7.5 quintillion. The number of stars in the observable universe is roughly 30,000 times larger than that. For every single grain of sand on Earth, there are 30,000 stars shining somewhere in the observable cosmos, and that is only the part of the universe we can see. The sheer scale of the observable universe is difficult to convey with numbers alone, so let us try an approach that brings it closer to lived experience. Suppose you wanted to count every star in the observable universe, one per second, without sleeping, without eating, without pausing for even a moment. How long would it take? At 1 star per second, counting 200 sextillion stars would require approximately 6.3 times 10 to the 15th years. That is 6.3 quadrillion years. The universe is currently 13.8 billion years old. Counting every star at 1 per second would take roughly 460,000 times longer than the entire current age of the universe. You would need to live through the complete history of the cosmos, from the Big Bang to the present moment, more than 400,000 times over, just to finish counting. And each of those stars is a real physical object, a sphere of burning plasma, many of them orbited by planets, some of those planets orbited by moons, some of those worlds perhaps harboring conditions suitable for life. The scale is not just large, it is incomprehensibly, overwhelmingly, staggeringly large. There is another way to sense this scale. If you could travel at the speed of a commercial jet aircraft, roughly 900 kilometers per hour, how long would it take to reach the edge of the observable universe? The answer is approximately 5.9 times 10 to the 19th years, or 59 quintillion years. At jet speed, reaching the edge of the observable universe would take roughly 4.3 billion times longer than the current age of the universe. Even at the speed of the fastest spacecraft ever built, the Parker Solar Probe at 635,000 kilometers per hour, the journey would take about 83 quadrillion years. These numbers are not just large, they are so large that the words we use to describe them, billion, trillion, quadrillion, lose their meaning. They become abstract placeholders for quantities that no human mind can truly grasp. To put the observable universe's size in more tangible terms, consider another scaled comparison. Imagine shrinking the cosmos down so that the Sun is the size of a single grain of sand, roughly 0.5 millimeter across. At that scale, the Earth would be a microscopic speck orbiting about 1.6 centimeters from the grain. Jupiter would be a slightly larger speck about 8.3 centimeters away. The nearest star, Alpha Centauri, would be another grain of sand approximately 4.5 kilometers distant. Our entire galaxy, the Milky Way with its hundreds of billions of stars, would be a vast collection of sand grains stretching across approximately 10,000 kilometers, roughly the width of the European continent, and the observable universe, at this scale, where our Sun is a single grain of sand, would be a sphere approximately 4.4 million kilometers in diameter. That is roughly 11 times the distance between the Earth and the Moon. A model of the observable universe, built at a scale where stars are grains of sand, would be larger than the Moon's orbit. The actual universe, at its true scale, is beyond all analogy. Now, here is where the foundation becomes critical. In 1929, an American astronomer named Edwin Hubble, working at the Mount Wilson Observatory in the mountains above Los Angeles, made one of the most important discoveries in the history of science. He was studying distant galaxies, using the observatory's 100-inch Hooker telescope, the largest in the world at that time. He was measuring their spectra, the specific wavelengths of light they emitted, and what he found was that almost every galaxy he observed had its light shifted toward the red end of the spectrum. This is called redshift, and it means the wavelength of the light has been stretched to longer values. Redshift in light works like the Doppler effect in sound. When an ambulance approaches you, the sound waves are compressed by the motion, and the pitch rises. When it moves away, the waves stretch, and the pitch drops. With light, the principle is the same. An object moving away from you has its light waves stretched, shifting them toward the red end of the visible spectrum. An object moving toward you has its light compressed, shifting it toward the blue end. Hubble found that distant galaxies were almost universally redshifted. They were receding from us. But the truly striking part was the pattern. The farther away a galaxy was, the faster it appeared to be receding. A galaxy twice as far away was moving roughly twice as fast. A galaxy 3 times as far was receding 3 times as fast. This was not random motion. It was a systematic, proportional relationship between distance and velocity. It was a pattern that demanded an explanation. And the explanation was profound. The universe was expanding. This relationship, now called Hubble's law, shattered the prevailing assumption of a static, eternal cosmos. Even Einstein, whose own equations of general relativity had predicted an expanding or contracting universe, had added a fudge factor to his equations, the famous cosmological constant, denoted by the Greek letter lambda, to keep the model static. He believed the universe should be unchanging. When Hubble's observations confirmed the expansion, Einstein reportedly called the cosmological constant his greatest blunder. The universe was not eternal and unchanging. It was dynamic, evolving, growing. The constant of proportionality in Hubble's law is called the Hubble constant, usually written as h0. Its current best estimate, derived from multiple independent observations, is somewhere between 67 and 74 kilometers per second per megaparsec. A megaparsec is a unit of distance equal to 3.26 million light-years. So, for every 3.26 million light-years of distance between us and a given galaxy, that galaxy appears to be receding from us approximately 70 kilometers per second faster. This relationship holds everywhere we look. The expansion is uniform, isotropic, meaning it appears the same in every direction. There is an important and unresolved puzzle here worth mentioning. Different methods of measuring the Hubble constant give slightly different answers, and those differences have persisted despite years of effort to resolve them. Measurements based on the cosmic microwave background, made by the Planck satellite in 2018, yield a value of about 67.4 kilometers per second per megaparsec. Measurements based on Type Ia supernovae and Cepheid variable stars in the local universe, led by Adam Rees and the SH0ES collaboration, yield a value of about 73 kilometers per second per megaparsec. The discrepancy is small in absolute terms but statistically significant. It exceeds 5 standard deviations, meaning there is less than a 1 in a million chance that it is due to random measurement error. This discrepancy is called the Hubble tension, and it has become one of the most debated problems in modern cosmology. Some researchers believe it will be resolved by identifying a subtle systematic error in one or both measurement methods. Others believe it may point to new physics beyond the standard cosmological model. Perhaps the expansion rate is not constant, but varies slightly depending on the epoch of the universe being measured. Perhaps there is an unknown component of the cosmos that affects the expansion differently at different times. We do not know. The tension remains. What we do know is that the expansion is real, regardless of the precise value of the constant, and the qualitative implications are the same whether the Hubble constant is 67 or 73. The universe is getting larger, the rate of expansion is accelerating, and beyond a certain distance, the recession velocity exceeds the speed of light. At small distances, this recession is modest. A galaxy 3.26 million light-years away is receding at about 70 kilometers per second. That is fast by everyday standards, but trivially slow compared to the speed of light. You would barely notice it. But the expansion is cumulative. It scales linearly with distance. A galaxy 32.6 million light-years away is receding at 700 kilometers per second. A galaxy 326 million light-years away is receding at 7,000 kilometers per second. A galaxy 3.26 billion light-years away is receding at 70,000 kilometers per second, or roughly 23% of the speed of light. And a galaxy 14 billion light-years away, near the edge of our cosmic horizon, is receding at approximately 300,000 kilometers per second. That is the speed of light itself. Beyond that distance, the mathematics does not stop. There is no cap, no ceiling, no break. Galaxies beyond the Hubble radius are receding from us faster than 299,792 kilometers per second. They are, in a very real and measurable sense, moving away from us faster than light. And this, astonishingly, does not violate Einstein's theories. To understand why, we need to grasp a distinction that Einstein himself built into the theory. Special relativity says that nothing can travel through space faster than light. No rocket, no particle, no signal can move from point A to point B through the fabric of spacetime at a velocity exceeding 299,792 kilometers per second. This is an absolute prohibition. But the expansion of the universe is not objects moving through space. It is space itself stretching. The galaxies beyond our horizon are not flying through space at superluminal speeds. They are essentially stationary in their local patch of space, while the space between us and them inflates. General relativity, Einstein's theory of gravity and spacetime, places no restriction on how fast space itself can expand. The speed limit applies to things moving through space, not to the behavior of space itself. This distinction is not a technicality. It is the fundamental reason that light speed is insufficient. The speed limit governs objects. It does not govern the stage on which those objects exist, and the stage is expanding without limit. The implications of this are staggering, and they form the central question of everything that follows tonight. If space can expand faster than light, then there are regions of the universe that are permanently unreachable. Light from those regions will never arrive here. Messages sent from those regions will never be received. Ships launched toward those regions will never arrive, and the boundary between what is reachable and what is not is invisible, intangible, and growing larger every moment. Something is deeply wrong with our intuitive understanding of the cosmos. We imagine the universe as a fixed arena, a stage on which stars and galaxies play out their roles. But it is not a stage. It is a living, expanding, dynamic fabric that creates new space between objects, even as those objects sit still. And the consequences of that expansion are, when fully understood, profoundly unsettling. What scientists discovered next was worse than anyone expected. The core problem can be stated simply, but its implications stretch across every domain of physics, every model of the cosmos, and every assumption we hold about what is possible. The universe is expanding, and the rate of that expansion means that most of the cosmos is already beyond our reach. Light speed, the theoretical maximum velocity for any piece of information or matter, is permanently insufficient to bridge the gap. To understand the full weight of this, we need to go deeper into the mechanics of expansion, the concept of the cosmic horizon, and the unsettling mathematics that governs everything. Let us begin with a common misconception that distorts the picture for many people. When they hear that the universe is expanding, they often picture something like an explosion, with galaxies flying outward from a central point into pre-existing empty space. Fragments of matter hurling away from ground zero. This image is comforting because it is familiar. It matches our experience with fireworks, with shrapnel, with anything that explodes. But it is almost entirely wrong. The Big Bang was not an explosion in space. It was an expansion of space itself. There was no central point. There was no pre-existing void into which matter was flung. There was no outside. Instead, all of space, everywhere, simultaneously, at every point, began to stretch. Every location in the universe was moving away from every other location. Not because the locations were flying through some fixed background, but because the background itself, the fabric of spacetime, was growing. New space was being created between every pair of points, uniformly, isotropically, everywhere at once. The best analogy, though it is imperfect, is the surface of a balloon being inflated. Imagine taking a deflated balloon and drawing small dots on its surface with a felt tip pen. Each dot represents a galaxy. Now begin to inflate the balloon. As the rubber stretches, every dot moves away from every other dot. No single dot is the center of the expansion. No dot is stationary while others move. The expansion is happening everywhere, on the surface simultaneously. Furthermore, dots that are farther apart move away from each other faster because there is more stretching rubber between them. This is precisely what Hubble's law describes. Distance is proportional to velocity because the expansion is uniform across the entire surface. But the balloon analogy has a critical limitation. It suggests a two-dimensional surface embedded in three-dimensional space. In reality, we are not on a surface. We are within three-dimensional space, and that space is expanding in every direction simultaneously. There is no edge, there is no boundary, there is no center. The expansion is not into anything. Space is not expanding into some larger container. There is no container. Space is all there is, and more of it is being created everywhere, all the time. The mathematics governing this expansion is described by the Friedmann equations, derived from Einstein's general theory of relativity by the Russian physicist and mathematician Alexander Friedmann in 1922. This was 7 years before Hubble's observational discovery of the expansion. Friedmann worked purely with the mathematics of general relativity and showed that a universe described by Einstein's equations could not be static. It had to be either expanding or contracting. There was no stable equilibrium. A static universe, balanced perfectly between expansion and contraction, would be like a ball balanced on the tip of a needle. Any perturbation, however slight, would send it one way or the other. The Friedmann equations describe how the scale factor of the universe, essentially a number that tracks how much space has stretched compared to some reference time, changes as a function of time. That change depends on the density of matter and energy within the universe. In the early cosmos, when matter and radiation were densely packed, the expansion was decelerating. Gravity, the attractive force between all matter, was pulling back on the expansion, slowing it down. This made intuitive sense. If you throw a ball upward, Earth's gravity decelerates it. The ball slows, stops, and falls back. The analogy for the universe was the same. Gravity should slow the expansion and might eventually reverse it. For decades, cosmologists debated the ultimate fate of the universe based on this deceleration. If the universe contained enough matter, gravity would eventually halt the expansion and pull everything back together in a big crunch, a mirror image of the Big Bang in which the cosmos collapsed to a single point. If the universe contained too little matter, the expansion would continue forever, decelerating but never stopping, and the cosmos would grow cold and thin and empty over infinite time. There was a critical density, a precise knife-edge value that separated these two fates. Measuring that density and determining whether the universe was above or below it was one of the central goals of 20th century cosmology. Then, in 1998, something happened that changed everything. Something so unexpected that the scientists who discovered it initially thought they had made an error. 2 independent teams of astronomers were studying a particular type of exploding star called a Type Ia supernova. The Supernova Cosmology Project, led by Saul Perlmutter at the Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rias at Johns Hopkins University, were both using Type Ia supernovae as distance markers. These explosions are useful because they occur when a white dwarf star accumulates enough mass from a companion star to reach a critical threshold, about 1.4 times the mass of the Sunday. At that point, the star detonates in a thermonuclear explosion of notably consistent brightness. Because the intrinsic brightness is nearly the same for every type E event, comparing the apparent brightness of a distant supernova to its known intrinsic brightness reveals how far away it is. They are cosmic standard candles, reliable measuring sticks for the vastness of space. By combining distance measurements from the supernova brightness with velocity measurements from the redshift, both teams could map how the expansion rate of the universe had changed over billions of years. They expected to find deceleration. They expected gravity to be winning. They expected the curve to bend downward, showing the expansion slowing over cosmic time. What they found was the opposite. The expansion of the universe was not decelerating. It was accelerating. Distant supernovae were dimmer than expected, meaning they were farther away than they should have been if the expansion were merely coasting or slowing down. The universe was not just growing. It was growing faster and faster with every passing eon. Both teams checked their data obsessively. They looked for systematic errors. They examined whether cosmic dust could be dimming the supernovae and mimicking the effect of greater distance. They cross-checked their calibrations. They scrutinized their statistical methods. The result held. The expansion was accelerating. The universe was being pushed apart by something. This discovery earned Perlmutter, Schmidt, and Reis the 2011 Nobel Prize in Physics. It also created an enormous problem for theoretical physics. If gravity is attractive, pulling matter together, then a universe filled with matter should be decelerating. Something was counteracting gravity on the largest scales. Something was generating a repulsive force that grew stronger as space expanded. That something was given the name dark energy, and despite more than 2 decades of effort, we still do not know what it is. Dark energy makes up approximately 68% of the total energy content of the universe. Let that figure register. More than 2/3 of everything that exists, in terms of energy, is composed of a substance we cannot identify, cannot detect directly, cannot create in a laboratory, and cannot explain from first principles. Ordinary matter, the protons, neutrons, and electrons that constitute every star, every planet, every living thing, every atom you have ever touched or seen, accounts for only about 5% of the cosmic energy budget. Dark matter, a separate mystery involving invisible mass that exerts gravitational attraction, but does not emit or absorb light, accounts for about 27%. The universe we see and touch is a thin froth riding atop a vast ocean of darkness. The most natural theoretical estimate for the value of dark energy, derived from quantum field theory, is catastrophically wrong. When physicists attempt to calculate the energy of the quantum vacuum, the seething ocean of virtual particles that fills all of empty space, they arrive at a number that is roughly 10 to the 120th power times larger than the observed value. That is a 1, followed by 120 zeros. This discrepancy, sometimes called the cosmological constant problem, has been described by the Nobel laureate Steven Weinberg as the worst prediction in the history of physics. It suggests that our understanding of quantum mechanics and gravity are fundamentally incomplete in ways we do not yet comprehend. The very substance that dominates the energy content of the universe and determines its ultimate fate is one we can neither explain nor calculate correctly. There is something deeply humbling about this. We have measured the expansion of the universe to exquisite precision. We have mapped the cosmic microwave background to 1 part in 100,000. We have catalogued billions of galaxies and measured their distances and velocities. But the dominant form of energy in the cosmos, the thing that is driving everything apart, remains a blank. We know its effects. We can model its consequences. But we do not know what it is, and it gets worse. The accelerating expansion driven by dark energy means that the cosmic event horizon, the boundary beyond which light can never reach us, is not merely a fixed limit. It is effectively tightening. The amount of the universe accessible to us, The volume we could in principle visit or communicate with given infinite time is decreasing. Galaxies that are currently visible through our telescopes are being pushed beyond the horizon by the acceleration. One by one, slowly but inexorably, the most distant objects in our observable sky will redshift into oblivion. Their light will be stretched to longer and longer wavelengths as the space between us and them expands. First, the visible light will shift to infrared, invisible to our eyes, then to microwave wavelengths, then to radio. Eventually, the wavelength will be stretched so far that no conceivable detector could ever capture it. The galaxies will fade from observability. Not because they have been destroyed, not because they have gone dark, simply because the space between us and them has expanded beyond the ability of their light to cross it. They will still be there, still shining, still full of stars and worlds and possibility, but permanently invisible to us. The process is not instantaneous. It unfolds over billions of years, but it has already begun, and it is irreversible. Astronomers have calculated that galaxies beyond a certain redshift threshold are already moving away from us faster than light. They are still visible because the light we see was emitted when they were closer, when the expansion had not yet carried them beyond the speed of light threshold. But no new light from those galaxies, no photon emitted today from their surfaces, will ever reach us. We are seeing their past, and their future is permanently hidden. Consider what this means in human terms. A person standing on a beach, watching a ship sail toward the horizon, knows that the ship will eventually disappear from view, but the ship still exists. It is merely beyond the line of sight. If the person climbed to a higher vantage point or used a telescope, they could see the ship again. The cosmic horizon is fundamentally different. There is no higher vantage point. There is no more powerful telescope. The ship is not merely beyond the line of sight. It is beyond the reach of causality. It is receding faster than any signal can pursue it. The ship is gone, not from view, but from physical reality as far as our universe is concerned. Let us put specific numbers to this process. The observable universe currently has a comoving radius of about 46.5 billion light-years. This is larger than you might expect for a 13.8 billion year old universe, because the space that the earliest light traveled through has expanded since that light was emitted. The light left the surface of last scattering, the boundary of the cosmic microwave background, when that surface was only about 42 million light-years from our location. But the 13.8 billion years of cosmic expansion since then have stretched that distance to 46.5 billion light-years. The observable universe is a sphere 93 billion light-years across, even though nothing has travelled faster than light. The cosmic event horizon, by contrast, is at a co-moving distance of about 16 to 17 billion light-years, depending on the specific cosmological parameters used. This is the maximum distance from which a signal sent today could ever reach us, or to which we could ever send a signal that would arrive. Everything beyond this distance is gone, not in the future. Now, it is already beyond our causal reach. The distinction between the observable universe and the reachable universe is crucial, and it is often overlooked. The observable universe is defined by how far light has travelled since the Big Bang. It is a record of the past. The reachable universe is defined by how far we could theoretically send a signal or a ship, given the current expansion rate and its acceleration. It is a measure of the future, and the reachable universe is considerably smaller than the observable one. We can see far more than we can touch. We possess images of galaxies that we could never visit, photographs of structures that are already beyond our causal horizon. Consider a specific example. The galaxy GN Z11, one of the most distant galaxies ever observed, was detected by the Hubble Space Telescope in 2016. The light we see from this galaxy was emitted approximately 13.4 billion years ago, when the universe was only about 400 million years old. At the time of emission, GN Z11 was roughly 2.7 billion light-years from our location. But the expansion of the universe has since carried it to a current distance of approximately 32 billion light-years. The galaxy is still there, presumably, still evolving, still forming stars. But it is 32 billion light-years away, deep beyond the cosmic event horizon. No signal we send today will ever reach it. No ship we launch will ever arrive there. The light we captured from it is a 13.4 billion year old photograph of a place that has moved beyond all possibility of contact. This creates a deeply strange and sobering picture of the cosmos. We can observe galaxies that we can never visit. We can measure their properties, analyze their chemical composition, determine their star formation rates, even estimate the masses of the black holes at their centers. But we cannot interact with them. They are spectral presences in our sky, real enough to photograph and study, but forever beyond the reach of any physical contact. They are there, and they are not there. They are visible, and they are inaccessible. The Laniakea supercluster, the massive structure of galaxies in which the Milky Way resides, spans roughly 500 million light-years and contains about 100,000 galaxies. It sounds enormous by any human standard, but within the observable universe's 9.3 billion light-year diameter, Laniakea is a tiny island. And even within that island, the expansion of space is at work. Galaxies on the outskirts of Laniakea are being tugged away from the core by the Hubble flow, the universal expansion. Over billions of years, many of them will drift beyond the gravitational reach of the supercluster and become permanently separated. The island will shrink. In the very far future, hundreds of billions of years from now, the only galaxies still gravitationally bound to the Milky Way will be those in our immediate local group. The Milky Way and Andromeda will have merged into a single large elliptical galaxy, sometimes nicknamed Milkomeda, in about 4 to 5 billion years. The other small galaxies of the local group, Triangulum, the Magellanic Clouds, and various dwarf satellites, will be absorbed or scattered. Beyond that small collection, everything else in the universe will have receded past the horizon. The sky will be empty. Now consider what this means for a hypothetical civilization that arises in that distant future, tens or hundreds of billions of years from now, in the merged remnant of the local group. That civilization would look out at the sky and see a single galaxy surrounded by empty darkness, no distant galaxies, no red-shifted light from receding clusters, no cosmic microwave background, because the radiation will have been stretched to wavelengths so long that no detector could capture it. There would be no observable evidence of the Big Bang, no Hubble law to discover, no expansion to measure, no way to infer the existence of dark energy. That civilization would construct its cosmology based on the only evidence available to it. It would conclude that the universe consisted of a single galaxy in an infinite, static void. It would have no way to discover that the cosmos was once teeming with trillions of galaxies, that the universe began with a hot, dense state, that space itself was expanding and accelerating. All of that evidence would have been erased, not by destruction, but by the expansion of space carrying it beyond the horizon of observation. This scenario was explored in detail by the cosmologists Lawrence Krauss and Robert Scherer in a 2007 paper. They pointed out that future observers would be cosmologically impoverished, not through any failing of intelligence or technology, but because the universe itself would have hidden the evidence. The expansion acts as a cosmic censor, progressively removing the clues to the universe's true history and structure. We live in a brief window of cosmic time when those clues are still visible. In 100 billion years they will not be. This cosmic censorship extends even to the physics of the universe's composition. Those future observers would have no way to detect dark energy, because there would be no distant galaxies to measure recession velocities against. They would have no way to discover dark matter's cosmological role, because the large-scale structure of the universe, the cosmic web of filaments and voids that reveals dark matter's gravitational influence, would be invisible to them. They would see only a single aging galaxy and would construct their physics accordingly. Their models would be internally consistent and experimentally verified. They would match all available data, and they would be fundamentally wrong. This raises a disturbing question that applies to us as well. Are we in a similar position? Is there evidence, crucial evidence about the nature of the cosmos that has already been erased by processes we cannot even detect. Is our cosmological model, for all its precision and predictive power, fundamentally incomplete because the universe has already hidden some of its secrets before we arose to look for them? We cannot know. And the fact that we cannot know is itself part of the problem. The universe does not announce what it has hidden. It does not leave a receipt for the evidence it has removed. It simply expands, and the evidence recedes, and the darkness grows. Let us return to the speed of light and what it means in this expanding context. A photon emitted from a distant galaxy today, one currently 12 billion light-years away, begins its journey toward us at 299,792 kilometers per second. But the space between that galaxy and Earth is expanding. By the time the photon has traveled a billion light-years toward us, the remaining distance has grown. The galaxy has not moved through space, but the space between the photon and Earth has stretched. The photon is like a swimmer in a river that is getting wider. Near the shore, the swimmer makes progress. But the farther the swimmer gets from the starting bank, the wider the river becomes, and the current strengthens. For galaxies beyond the cosmic event horizon, the river always wins. The photon swims forever but never arrives. It is perpetually in transit, carried further and further from its destination by the expanding space it moves through. The photon does not slow down. It maintains its speed of 299,792 kilometers per second in its local patch of space at every moment, but the total distance ahead of it grows faster than it can close the gap. The photon is running on a cosmic treadmill, and the treadmill is accelerating. The numbers are striking. Using the Hubble constant of roughly 70 kilometers per second per megaparsec, we can calculate the distance at which the expansion rate equals the speed of light. This distance is called the Hubble radius, and it currently sits at approximately 14.4 billion light-years. At that distance, space is expanding at exactly the speed of light. Beyond it, the recession velocity exceeds light speed, and because of the acceleration caused by dark energy, this is not a static boundary. Galaxies that are currently inside the Hubble radius are, over time, being pushed outside it by the accelerating expansion. The reachable volume of the universe is contracting. It is worth emphasizing one more time that this superluminal recession does not violate Einstein's theories. The prohibition in special relativity is against objects moving through space faster than light. The expansion of space is not movement through space. It is the creation of new space between objects. Imagine two ants on a rubber sheet that is being stretched. Each ant is stationary on the sheet. Neither ant is crawling. But the distance between them is increasing because the sheet is being pulled. The ants are not violating any speed limit. They are not moving at all in their local frame. But the distance between them is growing, and it can grow at any rate, including rates that correspond to superluminal recession. To make this even more concrete, consider a specific thought experiment. Suppose we could build a spacecraft capable of traveling at 99.99% of the speed of light. Suppose we launched it today toward a galaxy that is currently 20 billion light-years away, well beyond the cosmic event horizon. Our spacecraft would streak through space at nearly 300,000 kilometers per second. In its local neighborhood, it would be covering ground at an astonishing rate. But the total distance to the target galaxy would be growing. The expansion of the intervening space would add new kilometers to the journey faster than the spacecraft could close them. After a billion years of travel, the spacecraft would be further from the target galaxy than when it launched. After 1 trillion years, the gap would be wider still. 2000, the spacecraft would be making local progress but losing the global race. It is like running on a treadmill that is slowly, relentlessly accelerating. Every step moves your legs forward. You are running hard. You are covering distance on the belt beneath your feet. But the belt is speeding up, and eventually you are running at maximum speed while the belt moves even faster. You are running as fast as you can, and you are falling behind. Even at light speed itself, the situation is the same for destinations beyond the event horizon. A photon launched today toward those unreachable regions will never arrive. The photon will travel at 299,000 792 kilometers per second, through its local patch of space, forever, without ever reaching its target. It will be eternally in transit, perpetually swimming, never arriving. The speed of light, the cosmic maximum, is not enough. This creates a permanent fracturing of the universe into causally disconnected regions. The cosmos is not one connected whole in any practical sense. It is a collection of isolated domains, island universes within the larger whole, each able to observe only a tiny fraction of the total. Our observable universe, with its 2 trillion galaxies and 93 billion light-year diameter, is just one such domain. Others exist beyond our horizon, almost certainly, containing their own galaxies, their own stars, their own physics, their own possibilities. But we will never see them. Their light will never reach us, and our light will never reach them. Most cosmological models suggest that the full universe is vastly larger than the observable portion. Some estimates, based on the flatness of space as measured by the cosmic microwave background, suggest the full universe could be at least 250 times larger in radius than the observable sphere. Others, based on certain inflationary models, suggest it could be 10 to the 23 times larger or more. If these estimates are correct, then what we can see, this sphere of 93 billion light-years containing 2 trillion galaxies, is an almost infinitesimally small fraction of the whole. A grain of sand in a desert that stretches beyond imagination, and light speed is not fast enough to cross even the grain. There is a deep irony embedded in this fact. We live in the fastest universe possible, in the sense that the speed of light is the absolute maximum speed for any object, any signal, any causal influence. Nature has given us the fastest speed it can. It is hardwired into the structure of spacetime, and yet that maximum speed is hopelessly, laughably, cosmically inadequate for the task of traversing the universe. The cosmos has expanded beyond the reach of its own ultimate speed limit. It has, in a sense, outrun itself. The universe created a maximum speed, and then grew too large for that speed to matter. But here is what makes this truly terrifying. Faced with the realization that even light speed is insufficient to span the universe, humanity has not simply accepted defeat. Over the past century, physicists, cosmologists, engineers, and speculative thinkers have explored numerous theoretical avenues, searching for loopholes in the laws of physics, workarounds in the geometry of spacetime, or deeper truths that might permit us to overcome the light speed barrier. Each approach is fascinating in its own right. Each reveals something deep about the nature of reality, and each, ultimately, runs into fundamental limitations that may be permanent. The first approach is the concept of the warp drive, and it is perhaps the most famous attempt to cheat the speed of light. In 1994, a Mexican theoretical physicist named Miguel Alcubierre, then a postdoctoral researcher at Cardiff University in Wales, published a paper in the journal Classical and Quantum Gravity that startled the physics community. Alcubierre was not a science fiction writer spinning fantasies. He was a trained relativist working squarely within the mathematical framework of Einstein's general theory of relativity, and he demonstrated that, at least on paper, it was possible to construct a valid solution to Einstein's field equations that described a bubble of warped spacetime moving faster than light. The Alcubierre metric, as it came to be known technically, works by manipulating the geometry of space rather than propelling a ship through it. The key insight is drawn directly from the lesson of cosmic expansion itself. If space can expand faster than light on cosmological scales without violating relativity, then perhaps a localized version of that expansion could be engineered. The drive would contract space in front of the ship, pulling the destination closer, and expand space behind the ship, pushing the origin away. The ship itself would sit in a flat, undistorted bubble of normal spacetime. It would not be moving through space at all in any local sense. It would be stationary while the space around it rearranged. But the net effect would be superluminal travel. The bubble would surf through the surrounding spacetime at any desired speed. The elegance of this concept is remarkable. The occupants inside the bubble would feel no acceleration. They would not be subject to the devastating g-forces that would accompany any attempt to accelerate a physical object to near light speed. They would not experience the time dilation predicted by special relativity for objects moving at relativistic velocities. From their perspective, the journey would happen at normal time, in normal conditions, while the universe shortened the path ahead of them and lengthened the path behind. The mathematics is valid. Alcubierre's metric is a genuine solution to the Einstein field equations. There is no algebraic error, no logical gap, no violation of the mathematical framework. The solution exists within general relativity as surely as the Schwarzschild metric that describes black holes. But here is the problem. Knowing that a mathematical solution exists does not mean that the physical conditions required to produce it are achievable. And the conditions required by the Alcubierre drive are severe. To create a warp bubble, you would need a form of matter or energy with negative energy density. Not merely low energy, not merely a vacuum. Genuine negative energy, a substance whose energy is below zero, below even the energy of completely empty space. Normal matter and energy have positive energy density. They curve spacetime inward, producing gravitational attraction. Negative energy would curve spacetime outward, producing a kind of repulsion. It is this exotic curvature that the warp bubble requires. Does negative energy exist? In a limited sense, perhaps. Quantum field theory, the framework that describes the behavior of particles and fields at the smallest scales, predicts certain configurations in which the energy density can be negative relative to the surrounding vacuum. The most famous example is the Casimir effect, first predicted by the Dutch physicist Hendrik Casimir in 1948 and experimentally confirmed in 1997 by Steve Lamoureux at Los Alamos National Laboratory. When two uncharged, perfectly conducting plates are placed very close together in a vacuum, typically separated by less than a micrometer, the energy density between them is slightly lower than the energy density outside. The plates are pushed together by the difference in quantum vacuum fluctuations. This is sometimes interpreted as negative energy between the plates, though the interpretation carries nuance. The challenge is scale. The Casimir effect produces tiny amounts of energy difference across microscopic gaps. The Alcubierre drive would require negative energy in quantities that are, by any current measure, absurd. In Alcubierre's original 1994 formulation, the energy requirement was roughly equivalent to the entire mass energy of the planet Jupiter, but with a negative sign. That is approximately 1.9 times 10 to the 27th kilograms of mass, converted to energy via Einstein's equation, but negative. We have no way to produce such a quantity of negative energy. We have no theoretical framework that suggests it could be produced, stored, or shaped into the precise distribution the warp bubble demands. Subsequent work by other physicists attempted to reduce this energy requirement. In 1999, Chris van den Broek showed that modifications to the geometry of the bubble could reduce the negative energy needed by many orders of magnitude. In 2011, Harold White at NASA's Johnson Space Center proposed further modifications, including oscillating the warp bubble's thickness, that he claimed could bring the energy requirement down to something on the order of the mass energy of a few hundred kilograms. These claims generated considerable media excitement. But they were met with skepticism by much of the physics community. The fundamental requirement for exotic negative energy remained, and no modification of the bubble geometry changed that basic fact. And there are deeper problems still. In 2009, a team of physicists including Stefano Finazzi, Stefano Liberati, and Carlos Barcelo published an analysis showing that quantum effects at the walls of an Alcubierre bubble would be devastating. As the bubble moved through space, quantum vacuum fluctuations at the bubble boundary would build up into an increasingly intense pulse of radiation. This radiation would grow without bound as the bubble approached and exceeded the speed of light. By the time the bubble decelerated at its destination, the accumulated radiation would be so energetic that it would destroy anything inside the bubble and potentially anything near the destination as well. The warp drive would be a weapon, not a vehicle. Additionally, other analyses showed that the interior of the bubble would be causally disconnected from its walls. This means the pilot inside could not control the bubble. They could not steer it, accelerate it, decelerate it, or stop it. Once the bubble was formed and set in motion, the occupants would be passengers with no controls, trapped inside a structure they could not influence, heading for a destination they could not change, at a speed they could not adjust. Even setting aside all of these problems, there is the question of whether a warp drive could overcome the cosmic expansion we have been discussing. The Alcubierre bubble contracts space ahead and expands it behind. But across tens of billions of light years, the cosmological expansion is already contracting and expanding space on its own. A warp bubble would need to contract space that the universe is simultaneously expanding. Over vast distances, the cumulative expansion could overwhelm the bubble's local contraction. The warp drive, if it could be built at all, might be effective only over relatively short cosmic distances. It might not help with the fundamental problem of a universe that has outgrown the speed of light. The second theoretical avenue is wormholes. The concept was first described mathematically by Albert Einstein and Nathan Rosen in 1935 inches a paper examining the solutions of general relativity. They found that the equations permitted structures now called Einstein-Rosen bridges, connections between two distant points in spacetime through a shortcut, a tunnel through the fabric of reality itself. Rather than traveling the enormous distance through normal space between two galaxies, you could step into one mouth of the wormhole and emerge from the other mouth, potentially billions of light years away, almost instantaneously. The appeal is immediate and powerful. If the problem is that space is too large and expanding too fast for light to cross, then the solution is to bypass the space entirely. Go around it, cut through it. Find a doorway that opens directly to a faraway location without traversing the intervening distance. In principle, a wormhole would render the expansion irrelevant. You would not be racing the expansion. You would be sidestepping it. But wormholes face problems that are, in many ways, even more severe than those facing the warp drive. The first is stability. The Einstein-Rosen bridge, as originally described by Einstein and Rosen, is not traversable. It opens and pinches shut in a time shorter than it would take light to cross from one end to the other. Nothing can pass through. It is a mathematical curiosity, not a doorway. To hold a wormhole open long enough for anything to pass through, you would need, once again, exotic matter with negative energy density. The throat of the wormhole, the narrowest part of the tunnel, would collapse unless it was propped open by a substance that violated the normal energy conditions of general relativity. The same exotic matter required by the Alcubierre drive appears here too, suggesting that these two approaches are, at a fundamental level, related. Both require physics that we do not possess and may never possess. In 1988, the Caltech physicist Kip Thorne, along with his students Michael Morris and Ulvi Yurtseva, published an analysis of traversable wormholes in the American Journal of Physics. Their work was prompted by a charming request from the science fiction author Carl Sagan, who was writing his novel Contact and wanted a scientifically rigorous way to transport his protagonist across interstellar distances. Thorne's team showed that traversable wormholes were mathematically permitted by general relativity, but only under conditions that required exotic matter violating the weak energy condition. They laid out the specific requirements and noted, with characteristic scientific caution, that whether such conditions could be realized in nature was entirely unknown. Even if traversable wormholes could somehow be created, their practical challenges are immense. We have no known mechanism for creating a wormhole. The process would presumably require manipulating spacetime at extraordinarily high energies, perhaps at the Planck scale, where quantum gravity effects dominate. We do not have a complete theory of quantum gravity. We do not know how spacetime behaves at those scales. We cannot experiment there. We are guessing, educated guessing, but guessing nonetheless. Then there is the problem of placement. A wormhole connects 2 points in spacetime, but which 2 points? You cannot simply wish a wormhole into existence with its exit conveniently located near a galaxy you wish to visit. The connection would need to be established by some physical process, and that process would need to place the exit at the desired location. How would you get the exit there? You would need to transport it through normal space, and transporting anything through normal space is precisely the problem we are trying to solve. One speculative proposal suggests using naturally occurring wormholes, if they exist, that might have formed during the extreme conditions of the Big Bang or through quantum fluctuations at the Planck scale. These would be extraordinarily tiny, far smaller than an atom, probably on the order of the Planck length, about 1.6 times 10 to the negative 35 meters. To be useful, they would need to be enlarged, stabilized with exotic matter, and somehow connected to a desired destination. Each step in this chain is currently beyond our understanding, let alone our capability. In 2017, the physicists Ping Gao, Daniel Jeffries, and Aaron Wall showed that in certain theoretical frameworks involving quantum entanglement between two black holes, a traversable wormhole could be held open by the quantum correlations themselves without requiring classical exotic matter. This was a significant theoretical advance. However, the wormholes described in their work were microscopic, existing within a simplified theoretical framework called the ADS CFT correspondence, which describes a universe with different properties from our own. Whether their result could be scaled up to macroscopic wormholes in a realistic cosmological setting remains entirely unknown. There is also the problem of time. Even if a traversable wormhole could be created and stabilized, the time required to establish the connection would itself be limited by the speed of light. You would need to physically transport one end of the wormhole to the desired destination, and that transportation would be limited to subluminal speeds. If you wanted a wormhole connecting Earth to a galaxy 10 billion light-years away, you would first need to get one end of the wormhole to that galaxy. And getting anything to a galaxy 10 billion light-years away, at sublight speed through expanding space, is precisely the problem we are trying to solve. The wormhole might solve the return trip, but the initial setup requires solving the very problem it is meant to address. It is a bootstrapping problem with no obvious solution. And finally, there is the question of whether wormholes exist in nature at all. Despite extensive theoretical work, no observational evidence for wormholes has ever been found, no gravitational lensing signature, no anomalous spectral pattern, no unexplained connection between distant regions of space. Wormholes remain, for now, mathematical constructs permitted by the equations, but not confirmed by observation. The third approach is the concept of tachyons, hypothetical particles that always travel faster than light. The idea was given rigorous theoretical treatment in the 1960s by the physicists Alexa Myron-Belanyuk, Vijay Deshpande, and George Sudarshan, and later elaborated by Gerald Feinberg at Columbia University, who coined the term tachyon from the Greek word tachys, meaning swift. The concept emerges naturally from the mathematics of special relativity. Einstein's equations relate energy, momentum, and velocity for particles with mass. For normal particles, called tardions, the equations impose the speed of light as an upper limit. As a tardion accelerates toward light speed, its energy approaches infinity. Reaching light speed would require infinite energy. Exceeding it is impossible. But Feinberg noticed that the equations also permitted solutions for particles with imaginary mass. Not imaginary in the sense of fictional, but in the mathematical sense, a mass whose square is a negative number. Such particles would always travel faster than light. They could never decelerate to light speed, just as normal particles can never accelerate to it. Light speed would be a barrier from both sides. Normal particles are trapped below it. Tachyons are trapped above it. The two populations can never cross the boundary. If tachyons existed, they could in principle carry signals faster than light. They would outrun the expansion. They would bypass the cosmic horizon. They would connect the disconnected regions of the universe with superluminal communication channels. But the problems with tachyons are fundamental and severe. First, and most simply, they have never been observed. No experiment, no particle accelerator, no cosmic ray detector, no astrophysical observation has ever produced evidence of a tachyon. Despite decades of looking, the particle remains entirely hypothetical. Second, and far more critically, the existence of tachyons as faster-than-light information carriers would violate causality. Special relativity shows that if a signal can travel faster than light, then there exist reference frames, valid observers moving at ordinary velocities for whom the signal arrives before it was sent. This is not a paradox that can be resolved by clever bookkeeping. It is a fundamental breakdown of cause and effect. If I can send a message to you that arrives before I sent it, then you could reply to me before I sent the original message. You could warn me not to send it. But then, why did you receive it? The logical structure of events collapses. Most modern physicists who encounter tachyonic fields in their equations interpret them differently than the naive faster-than-light picture suggests. In quantum field theory, a tachyonic field is not a field of particles zipping around faster than light. It is a field sitting at an unstable maximum of its potential energy, like a ball balanced on top of a hill. The tachyonic nature signals that the field will roll down to a stable minimum, undergoing what is called spontaneous symmetry breaking. The famous Higgs field before the electroweak phase transition in the early universe was technically tachyonic, but the Higgs mechanism did not produce faster-than-light particles. It produced the Higgs boson, which travels at sublight speeds like every other massive particle. So tachyons, as superluminal vehicles for crossing the universe, almost certainly do not exist. And even if they did, the causality violations they would introduce might make them useless for any practical purpose. You cannot build a useful communication system on a channel that destroys the distinction between past and future. The fourth approach is quantum entanglement, which is often misunderstood by the public as a form of faster-than-light communication. Quantum entanglement is a genuine, experimentally verified phenomenon. It is real, it is weird, and it is not what most people think it is. When two quantum particles become entangled, their quantum states become correlated in a way that has no classical analog. Measuring the spin of one particle, for example, instantly determines the spin of the other, regardless of the distance separating them. There is no signal traveling between the particles. There is no delay. The correlation is established immediately, at the moment of measurement, across any distance. Einstein, who was deeply troubled by this phenomenon, called it spooky action at a distance. He believed it indicated that quantum mechanics was incomplete, that there must be hidden variables determining the outcomes in advance. In 1964, the physicist John Bell showed that this interpretation was wrong. The correlations in entanglement are genuinely non-local. They cannot be explained by any local hidden variable theory. The universe really does exhibit this kind of instant-distant correlation. This sounds like it should solve the light speed problem. If entanglement creates instant correlations across unlimited distances, why not use it to communicate faster than light? Encode a message in the spin measurements of entangled particles here, and read it out from the partner particles in a distant galaxy. Bypass the light speed limit entirely. Bypass the expansion. The answer is the no communication theorem, one of the most important results in quantum information theory. While entanglement creates real, verified, instantaneous correlations, those correlations cannot be used to transmit information. The reason is deeply rooted in the structure of quantum mechanics. When you measure an entangled particle, you get a random result. The randomness is not a reflection of your ignorance. It is fundamental. You cannot choose what result to get. You can only observe what nature provides. The person at the other end of the entanglement also gets a random result, perfectly correlated with yours, but indistinguishable from pure randomness without comparing the two sets of measurements. And comparing measurements requires sending a classical message limited to the speed of light. The no communication theorem was proven rigorously in 1982 by the physicists Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber. It shows that the reduced density matrix of one half of an entangled system is unaffected by any measurement performed on the other half. In plain language, nothing you do to your particle here changes the statistical distribution of results that the distant observer sees there. They see random outcomes either way. The correlations are real but invisible until the two sets of results are brought together, which requires a classical channel, which is limited to light speed. This result has been tested experimentally many times. In 2015, a team led by Ronald Hansen at the Delft University of Technology in the Netherlands performed a loophole-free Bell test. confirming entanglement correlations across a distance of 1.3 kilometers, with all known loopholes closed. The correlations were exactly as quantum mechanics predicted. The no communication theorem held perfectly. Entanglement is real and non-local, but it carries no information. To use a simple analogy, imagine two people, each given a sealed envelope from the same source. When they open their envelopes simultaneously, they always find the same number inside. The correlation is perfect and instantaneous, but neither person can control what number appears. They cannot encode a message in the envelope system. The envelopes carry correlation, not communication. Entanglement is the same. It is a correlation channel, not a communication channel. The math is striking when you consider the implications. Nature has provided a phenomenon that is genuinely non-local, genuinely instantaneous, and genuinely useless for sending messages. It is as if the universe has teased us with a mechanism that seems to violate the speed of light, only to reveal that the violation is precisely in the dimension that does not matter. Entanglement connects, but it does not communicate. The fifth approach is perhaps the most speculative and the most dangerous. It involves the idea of manipulating the expansion of space itself. If the problem is that space is expanding too fast for light to cross, then perhaps the solution is to slow, halt, or reverse the expansion in a local region. If you could create a corridor of non-expanding space between Earth and a distant galaxy, then light, or a spacecraft, could traverse that corridor without fighting the expansion. The distance would remain fixed. The journey would be possible. This idea connects to some of the deepest unresolved questions in physics. What is dark energy? Is it a cosmological constant, a fixed property of spacetime itself that cannot be changed? Or is it a dynamic field, sometimes called quintessence, that might be mutable? If it is a cosmological constant, then it is as fundamental as the speed of light or the gravitational constant. You cannot change it any more than you can change the charge of an electron. It is woven into the equations at the deepest level. But if dark energy is a dynamic field, then in principle it might be manipulable. You could imagine, in the most speculative and distant future, a technology that could alter the local value of the dark energy field, suppressing the expansion in a specific region of space. This would be engineering at the cosmological scale, manipulating the fundamental properties of spacetime itself. The problems with this idea are immense. First, we do not know what dark energy is. We cannot manipulate something we do not understand. Second, even if dark energy is a dynamic field, the energy required to alter it over cosmic distances would be beyond comprehension. Third, there is the danger of catastrophe. If the current vacuum state of the universe is not the lowest energy state, if it is what physicists call a false vacuum, then perturbing it could trigger a transition to the true vacuum. This transition would propagate at the speed of light as a bubble of new vacuum, a region where the laws of physics might be fundamentally different. Inside that bubble, atoms might not be stable, chemistry might not work, life would be impossible. The bubble would expand forever, consuming everything it touched. This is not a tool for exploration. It is a potential extinction mechanism for the universe itself. There is a sobering irony in this last approach. The most ambitious attempt to overcome the expansion of space, by manipulating the properties of the vacuum itself, carries the risk of triggering a catastrophe that would make the original problem irrelevant. You cannot outrun the expansion if your solution destroys the runners. Beyond these 5 main approaches, there are scattered speculative ideas at the fringes of theoretical physics. Some researchers have explored whether closed time-like curves, paths through spacetime that loop back to their starting point in time, might allow information to circumvent the expansion by traveling backwards in time and then forward along a different path. But closed time-like curves bring their own severe problems, including the potential for grandfather paradoxes and the violation of every principle of causation that physics relies upon. The physicist Stephen Hawking proposed what he called the chronology protection conjecture, suggesting that the laws of physics conspire to prevent the formation of closed time-like curves. If he was right, then time travel is another door that physics has firmly closed. Others have wondered whether the laws of physics themselves might change in the far future, perhaps providing new mechanisms that do not currently exist. Perhaps a phase transition in the fundamental forces could alter the speed of light itself or change the nature of the expansion, but these are speculations without any supporting evidence. They are hopes dressed in the language of physics, wishes for a future rescue by laws we do not know and have no reason to expect. Each of these 5 approaches, the warp drive, the wormhole, the tachyon, the entanglement channel, and the vacuum manipulation, represents the best that human theoretical physics has offered against the light-speed barrier. Each is grounded in real science, at least at its point of departure. Each has been studied by serious researchers at serious institutions, and each encounters obstacles that may be fundamental and permanent. The warp drive requires exotic negative energy that we cannot produce and may not exist in useful quantities. The wormhole requires the same exotic matter plus a construction method we cannot even theorize. Tachyons violate causality and have never been observed. Entanglement is real but cannot carry information. Vacuum manipulation could destroy everything. This is not a failure of imagination. This is a confrontation with the structure of reality itself. The universe appears to have been built with a speed limit, and it has grown too large for that speed limit to bridge its reaches. Every workaround we have conceived runs into a wall not of technology but of physics. The universe, it seems, was not designed to be crossed. It was not built with doors between its rooms. It was built with rooms that drift apart, forever, faster than any occupant can walk between them. There is a way to frame this that captures its full weight. Imagine that every physics department in every university on Earth, every theoretical physicist, every engineer, every space agency, every private company, every nation pooled all of their resources, all of their knowledge, all of their creativity, and devoted everything to the single goal of sending one atom to the other side of the observable universe. Not a spacecraft, not a person, just one atom, one hydrogen nucleus, one proton. With the combined effort of every human being who has ever lived, every joule of energy that humanity has ever generated, every insight that every scientist has ever had, the task would remain impossible. The distances are too vast, the expansion is too fast, the speed limit is too low. One proton across 93 billion light-years through expanding space. We cannot do it. And no technology will change the underlying physics that prevents it. And this is where the answer becomes deeply unsettling. The deeper truth is not about speed. It is not about engines, energy sources, exotic particles, or the limitations of our technology. It is about something more fundamental. It is about information. The real barrier imposed by the expansion of the universe is not a barrier to travel. It is a barrier to knowledge. The universe is not merely too large to cross, it is too large to know. This distinction matters more than it might initially seem. Throughout human history, we have encountered barriers to travel. Oceans, mountain ranges, deserts, polar ice caps, the vacuum of space between worlds. In every case, eventually, we found a way across. We built canoes, then sailing ships, then steamships. We carved roads through mountains and tunneled beneath them. We built aeroplanes that leapt over deserts and helicopters that reached polar research stations. We built rockets that carried people to the moon. Every barrier, no matter how formidable, eventually yielded to human ingenuity, courage, and persistence. This is the story we tell ourselves. This is the narrative that defines our species. We are the ones who cross barriers. But the barrier imposed by the expansion of the universe is different in kind, not merely in degree. It is not a wall that might crumble with enough force. It is not a gap that might be bridged with enough engineering. It is a limit built into the geometry of spacetime itself, into the mathematical structure of the cosmos, and it does not just prevent us from going somewhere, it prevents us from ever knowing what is there. It is not a physical barrier, it is an informational one. And informational barriers are, in a very real sense, absolute. Consider what it means to observe a distant galaxy. When we train the James Webb Space Telescope or the Hubble Space Telescope on a galaxy 10 billion light-years away, we are not seeing that galaxy as it is now. We are seeing it as it was 10 billion years ago, when the light we are capturing first left its stars. The farther we look into space, the further we look back into time. This is not a limitation of our instruments. It is a fundamental property of a universe in which information travels at a finite speed. The speed of light is not just a speed limit for objects, it is a speed limit for knowledge. But the expansion of the universe adds a cruel twist. The galaxy that emitted the light 10 billion years ago is no longer 10 billion light-years away. Space has been expanding for the entire time the light was in transit. By now, that galaxy has been carried to a current distance of perhaps 20 or 25 billion light-years, depending on the cosmological parameters used. We see the galaxy where it was, not where it is. And where it is now may already be beyond our cosmic event horizon. We have a photograph of a place we can never visit, a postcard from a sender we can never reply to. This creates a deeply unsettling epistemological situation. We can observe galaxies that we can never interact with. We can photograph them, measure their spectra, determine their chemical compositions, estimate the masses of their central black holes, count their star-forming regions, even infer the presence of exoplanets orbiting their stars. But we cannot send a message to any of them. We cannot receive an updated image. We are looking at frozen moments in the history of places that have long since moved beyond our reach. They are ghosts in our telescopes. Bright, detailed, scientifically analyzable ghosts, but ghosts nonetheless. Let that sink in. The universe shows us things it will never let us touch. It reveals its past while concealing its present. It offers us images of beauty and grandeur and then tells us, through the mathematics of expansion, that the originals are gone. The light we captured is a message from the past, delivered from a sender who has moved to an address we can never reach. Now extend this to the cosmic microwave background, the oldest light in the entire universe. This radiation was emitted approximately 380,000 years after the Big Bang, at a moment called recombination, when the universe cooled enough for the first hydrogen atoms to form and for photons to finally travel freely through space without being constantly scattered by free electrons. Before recombination, the universe was an opaque fog of hot plasma. After recombination, it became transparent. The first light was released, and it has been traveling through the expanding cosmos ever since, cooling as space stretched it to longer and longer wavelengths. Today, that light arrives at our detectors as microwave radiation with a temperature of approximately 2.725 Kelvin, just 2.725 degrees above absolute zero. The cosmic microwave background is our deepest window into the past. It shows us the universe as it was when it was only 380,000 years old, less than 0.003% of its current age. The surface from which this light was emitted is called the surface of last scattering. At the time of emission, that surface was only about 42 million light-years from our current location. But the intervening 13.8 billion years of cosmic expansion have stretched that distance enormously. The surface of last scattering is now approximately 46.5 billion light-years away. It defines the boundary of our observable universe. What lies beyond that boundary? Almost certainly, more universe. The standard models of cosmology, backed by the extraordinary uniformity of the cosmic microwave background, which is the same in every direction to a precision of 1 part in 100,000, strongly suggest that the universe extends far beyond what we can observe. The same physics, the same types of galaxies, the same distribution of matter and energy, but we can never verify this. We can never see past the cosmic microwave background. Before that epoch, the universe was opaque. No light from earlier times reaches us in any form we can detect, and we can never see objects whose light has been stretched to undetectable wavelengths by the expansion. The informational horizon is total. It is not like a mountain that blocks your view, where you could climb to a higher vantage point and see over the top. There is no higher vantage point. There is no angle, no wavelength, no type of radiation, no gravitational signal, no neutrino flux, no conceivable instrument that can see past the edge of the observable universe. The edge is not a physical object. It is not a wall or a barrier or a fence. It is the boundary of causality itself. It is the frontier beyond which no event has had time to create any effect at our location. Nothing from out there has influenced anything in here, and nothing from in here can influence anything out there. This is not science fiction. This is the measured, verified, mathematically rigorous reality of the cosmos, as described by general relativity and confirmed by decades of precision observation using instruments including the COBE satellite launched in 1989, the WMAP satellite launched in 2001, and the Planck satellite launched in 2009. The precision of these measurements deserves emphasis. The Planck satellite, operated by the European Space Agency, measured the temperature of the cosmic microwave background across the entire sky to a precision of a few millionths of a degree. It mapped the tiny fluctuations in that temperature, the seeds from which all cosmic structure, every galaxy, every cluster, every supercluster, eventually grew. Those fluctuations are at the level of 1 part in 100,000. The universe, at the time the cosmic microwave background was emitted, was extraordinarily uniform, almost perfectly smooth. But not quite perfectly smooth. The tiny deviations from perfect uniformity, amplified by billions of years of gravitational collapse, became the galaxies and galaxy clusters we observe today. From those measurements, combined with observations of distant supernovae, galaxy surveys, and measurements of large-scale structure, cosmologists have built what is called the lambda CDM model, or the Standard Model of Cosmology. Lambda refers to the cosmological constant representing dark energy. CDM stands for cold dark matter. The model has 6 free parameters, and it fits an extraordinary range of observations with remarkable precision. It is one of the most successful models in all of science. It tells us the age of the universe to within 1%. It tells us the composition, the geometry, the expansion rate, the history. It is a triumph of human understanding. And it tells us, without ambiguity, that the universe is expanding and will continue to expand forever. The expansion will accelerate, the galaxies will recede, the horizon will close in. The evidence will be erased. This is not speculation. It is the direct prediction of the best-tested cosmological model we have. And the implications extend far beyond the present moment. Because the expansion is accelerating, the cosmic event horizon is, in practical terms, tightening. The volume of the universe from which signals can ever reach us is shrinking. Every year, every day, every passing second, galaxies that were within our theoretical causal reach are slipping beyond it. The horizon is not static. It is closing in around us like a slowly contracting sphere of possibility. In the very far future, trillions of years from now, the accelerating expansion will have pushed every structure beyond the local group past the cosmic event horizon. The merged remnant of the Milky Way and Andromeda galaxies will hang alone in an apparently infinite void. An observer at that time would look out at a sky with no external galaxies visible. The cosmic microwave background radiation, stretched to wavelengths of kilometers or more, would be utterly undetectable. There would be no observable evidence of the Big Bang, no redshifted galaxies to discover, no Hubble law to measure, no expansion to infer. Every clue to the true nature and history of the cosmos would have been erased. The cosmologists Lawrence Krauss and Robert Scherer explored this scenario in a paper published in 2007. They demonstrated that a civilization arising in that far future would have no way to discover the fundamental truths of cosmology that we consider established. They would be intelligent, perhaps more intelligent than us. They would have advanced technology, perhaps far more advanced than ours, but the universe would have hidden the evidence. The expansion would have carried the proof beyond all observation. The cosmos censors its own history. Let that sink in. The universe is not merely indifferent to our desire to explore it. It is actively erasing the record. It is a library that is burning its own books, not through fire, but through the relentless stretching of space that carries the pages beyond the reach of any reader. This raises questions that are both scientific and philosophical. How much of reality are we already missing? If the observable universe is only a tiny fraction of the full cosmos, then there may be entire categories of physical phenomena that occur beyond our horizon and that we will never detect. There may be structures so large that they dwarf anything in our observable sphere. There may be regions where inflation proceeded differently, where the vacuum settled into a different state, where the constants of nature have different values. Some inflationary models, particularly the eternal inflation model proposed by Alexander Vilenkin and further developed by André Linde, suggest that the universe is constantly generating new pocket universes with potentially different physical laws. If this is true, then what we call the universe is merely one bubble in an infinite foam of realities, each with its own physics, its own chemistry, its own possibilities. But we can never observe the other bubbles. They are beyond all horizons, separated from us not just by distance but by the ongoing inflation of the spaces between. The eternal inflation scenario, if correct, transforms the nature of the problem entirely. It is not merely that the universe is too large to cross. It is that there may be an infinite number of universes, each too large to cross, each forever isolated from the others, each containing its own potentially unique version of physics. The multiverse, as this collection is sometimes called, is not a place you could explore. It is an infinite collection of places that can never interact. Within each pocket universe, civilizations might arise, look out at their own cosmic microwave background, measure their own Hubble constant, and discover their own version of the problem we are discussing tonight. They would find that their own speed of light, whatever its value might be in their vacuum state, is insufficient to cross their own cosmos. They would be trapped inside their own bubble, just as we are trapped inside ours. And between the bubbles, the inflationary expansion would continue forever, creating new bubbles, each isolated, each unreachable. This is, by any standard, a staggering vision of reality. An infinite foam of universes, each containing possibly infinite space, each expanding, each isolating its inhabitants from all others, forever. And the speed of light in every one of them is insufficient. The epistemological implications are profound. Science is founded on observation and experiment. Theories are proposed, predictions are derived, and those predictions are tested against measured data. But what happens when the data is fundamentally incomplete? When the universe withholds evidence not through any physical mechanism we could overcome, but through the geometry of space-time itself? Are we doing science? Or are we doing local science, provincial science, science that applies to our patch of reality, but might not generalize to the whole? There is a principle in cosmology called the Copernican principle, which holds that our position in the universe is not special. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the center of the universe. By extension, our observable patch should be representative of the cosmos at large. The Copernican principle is supported by the near-perfect isotropy of the cosmic microwave background. The universe looks the same in every direction to extraordinary precision. This suggests uniformity. But uniformity within our bubble does not prove uniformity beyond it. The Copernican principle is an assumption, not a theorem. It is a reasonable assumption given the data we have. But we do not have data from beyond the horizon. We are extrapolating. We are assuming that the sample is representative. And the sample is a single point, a single observation post, a single bubble of light in an ocean of darkness that might be uniform or might be wildly diverse. We cannot tell. We are prisoners of our light cone. The light cone is a central concept in special relativity, describing the region of spacetime causally accessible to a given observer. Your past light cone encompasses every event whose influence has had time to reach you. Your future light cone encompasses every event you could theoretically influence. In a non-expanding universe, the light cone grows forever, eventually encompassing everything. But in an expanding universe, the light cone is bounded. It reaches a maximum size and then, in some models, shrinks as the expansion pushes the most distant events beyond causal reach. Our future light cone, the set of events we could in principle influence or observe, is finite and contracting. There are things in the universe that we will never affect and never detect. There are events that will happen, are happening now that will never leave any imprint on our reality. They are as remote from us as if they occurred in a different universe entirely, and in a meaningful physical sense, they do. The concept of the light cone has a visceral impact when you consider it in terms of communication. Suppose an advanced civilization exists in a galaxy that is currently 20 billion light-years away, well beyond our cosmic event horizon. Suppose they have solved all the problems of physics that we have not. Suppose they know the nature of dark energy, the structure of quantum gravity, the solution to every open problem. They could hold the answers to every question we have ever asked, and we will never know. Their knowledge exists. It is real. It is out there. But the expanding space between us ensures that no photon, no gravitational wave, no neutrino, no signal of any kind carrying that knowledge will ever reach our detectors. The answers are written in a book we cannot open, in a library we cannot visit, in a language we will never hear. This is the deeper truth. The speed of light is not merely a speed limit, it is a knowledge limit. The expansion of the universe is not merely a physical process, it is an epistemological boundary. It defines not just where we can go, but what we can know, and what we can know is far, far less than what exists. We are temporary patterns in matter and energy, briefly complex enough to apprehend the shape of our confinement. We have learned enough physics to understand that we cannot learn all physics. We have seen enough of the cosmos to understand that we cannot see all of it. The universe has shown us its splendor and then drawn a curtain around the rest, a curtain made of expanding spacetime that no observation can penetrate and no force in nature can pull aside. Some might find this revelation depressing, a shrinking of possibility, a closing of doors. Others might find it humbling, a reminder of our smallness against the vastness of what exists. But there is a third response, one perhaps more suited to the kind of minds that probe the cosmos at 3 a.m. We can find it beautiful. The universe is larger than understanding. It exceeds not just our reach, but our capacity for knowing. And yet, within our tiny observable patch, within our brief window of cosmic time, we have managed to figure out the shape of the limitation. We have named the darkness beyond our horizon. We have described its mathematical boundaries. We have built instruments that capture photons from the very edge of observability and use them to reconstruct the history of creation. We cannot cross the universe. We cannot see all of it. We cannot know what lies beyond the horizon. But we know the horizon is there, and that knowledge, fragile and provisional as it is, represents a triumph. There is a particular quality to this kind of knowledge that sets it apart from most of what science discovers. Most scientific knowledge empowers. It tells us how to build, how to cure, how to predict, how to control. The knowledge we have been discussing tonight is different. It is knowledge of limits. It tells us what we cannot do, what we cannot reach, what we cannot know, and yet this knowledge is no less valuable. Perhaps it is more so. To understand the boundary of the knowable is to understand the shape of knowledge itself. To see the edge of the visible is to grasp something about the nature of vision. The universe has given us the extraordinary gift of understanding, and then shown us the boundary beyond which understanding cannot go. Both gifts are remarkable. Both are worth receiving. The universe is silent beyond the horizon, but within it, for a little while longer, there are minds that can hear the silence and understand what it means. What does it mean to live in a universe that cannot be crossed? What does it mean for a species that defines itself by exploration, by the drive to push past every boundary, to discover that there exists a boundary that is absolute? These are not merely scientific questions. They are existential ones. They touch the deepest layers of how we understand our place in the cosmos, our relationship with time, our hopes for the future, and our understanding of what it means to be alive in a reality of this particular shape and character. For most of human history, the question would have been meaningless. Our ancestors inhabited a world bounded by the horizon of their senses. The edge of the known world was the edge of vision, the limit of a sailing voyage, the farthest mountain they could see on a clear day. Each generation pushed the boundary outward. The Polynesians navigated thousands of miles of open ocean using the stars and the patterns of waves, reaching islands that no previous generation had known existed. The Phoenicians circumnavigated Africa more than 2,000 years before Europeans attempted it. The Chinese treasure fleets of the 15th century explored the Indian Ocean on a scale that dwarfed contemporary European voyages. Each expansion of the known world reinforced a compelling narrative. There are no permanent barriers. Every boundary is temporary. Every limit is an invitation. That belief carried us into the modern era. It carried us into the age of aviation, when the Wright brothers flew for 12 seconds at Kitty Hawk in 1903, and within 66 years, less than a single human lifetime, their intellectual descendants had walked on the moon. It carried us into the space age, when the Soviet Union launched Sputnik in 1957, and the United States responded by building the Saturn V rocket, the most powerful machine ever constructed, and using it to send human beings across 384,000 kilometers of vacuum to stand on another celestial body. It carried our robotic emissaries further still. Voyager 1, launched in 1977, is now more than 24 billion kilometers from the Sun, having left the heliosphere, the bubble of solar wind that defines our star's influence, and entered the interstellar medium. At that distance, the Sun is just another bright star, and yet Voyager has crossed less than 1/10,000th of the distance to the nearest star. It is still, in cosmic terms, at home. The expansion of the universe tells us that the pattern of ever-expanding horizons does not continue forever. There are limits that are not technological but structural, not barriers we have not yet overcome but boundaries we cannot overcome in principle. The universe is not a room with walls that we might one day break through. It is a room whose walls are receding faster than we can approach them. No amount of cleverness, no leap of engineering, no revolution in physics as currently understood changes this. The walls are made of expanding space, and space does not care about our ambitions. This realization carries weight. We are a species that tells itself stories about the frontier. The frontier is central to mythology, to literature, to the founding narratives of entire civilizations. The American frontier, the maritime frontier, the space frontier. In each case, the story follows the same arc. A vast unknown lies beyond the edge of the known world. Brave individuals venture into it. They discover wonders, face dangers, and expand the domain of human knowledge and habitation. The frontier recedes, but it never vanishes. There is always more to explore. The cosmic frontier is different. It is a frontier that is, mathematically and physically, unreachable. The galaxies beyond the cosmic event horizon are not undiscovered countries waiting for explorers. They are countries that are moving away faster than any explorer can travel. The frontier is not merely distant, it is actively fleeing. Intimae. How does a frontier species absorb this? How does a species built on the myth of infinite horizons make peace with a horizon that is final? Perhaps by redefining what exploration means. Perhaps the deepest form of exploration is not the crossing of physical distances but the mapping of conceptual landscapes. We explore not only with ships and rockets but with mathematics, with telescopes, with the architecture of theory. The observable universe, even confined within its 9.3 billion light-year diameter, contains enough mystery to occupy every curious mind that will ever exist. There are black holes whose interiors obey laws we do not yet understand. There are neutron stars so dense that a teaspoon of their matter would weigh 1 billion tons. There are galaxies colliding in slow motion across hundreds of millions of years, producing gravitational tides that reshape the fabric of space. There are dark matter halos, invisible scaffolding of mass that gives galaxies their structure, whose nature remains one of the great open questions in physics. There are exoplanets with atmospheres that hint at chemistry we have never seen, orbiting stars whose properties challenge our models of stellar evolution. Within our own solar system alone, there are mysteries sufficient for centuries of investigation: the oceans beneath the ice shells of Europa and Enceladus, the methane lakes of Titan, the geological complexity of Mars, the atmospheric dynamics of Jupiter and Saturn. Each of these is a world unto itself, a place with its own history, its own processes, its own unanswered questions. We have barely begun to explore our own cosmic backyard, let alone the galaxy, let alone the observable universe. And within the domain of physics itself, there are theoretical landscapes as vast as any physical one. The nature of dark matter, which constitutes 27% of the cosmos and whose particles we have never identified. The mechanism of dark energy, which drives the very expansion we have been discussing tonight, and which remains profoundly mysterious. The reconciliation of quantum mechanics and general relativity, the two greatest theories in physics, which are individually successful but mutually incompatible when pushed to extremes. The information paradox of black holes, which threatens the most fundamental principle of quantum mechanics. The origin of the matter-antimatter asymmetry that permits the existence of the material universe. Each of these questions is a frontier as challenging and as rewarding as any physical voyage. The observable universe is not a prison. It is the largest laboratory that any species has ever been given access to. Within it, the questions are inexhaustible, the mysteries are bottomless, the beauty is overwhelming. And there is the matter of other minds. If the universe contains other intelligent civilizations, then many of them are separated from us by the cosmic event horizon. We will never meet them. We will never detect their signals. We will never share our knowledge or receive theirs. Each civilization, no matter how advanced, is confined to its own observable bubble. But they all inhabit the same physics. They all measure the same cosmic microwave background. They all discover the same expansion. They all confront the same limit. There is a strange solidarity in this. A communion of isolated minds, separated by distances that light itself cannot bridge, but united by the shared experience of discovering that they are separated. This is perhaps the most poignant implication of all. The universe may be teeming with intelligence, alive with thought, rich with civilizations that have answered questions we have not yet thought to ask. And we will never know, not because we are too primitive, not because we lack the technology, but because the geometry of spacetime will not permit it. The universe has placed each thinking mind inside its own light cone, its own bubble of causality, and drawn the horizons tight. Each mind looks out at its own visible sky and wonders if it is alone. And the answer might be no, might be gloriously, beautifully no. But the evidence is on the other side of an uncrossable divide. We are all, everywhere, alone together, separated by expanding space, connected by the universality of the physics that separates us. There is a final philosophical dimension worth sitting with. The fact that the universe is larger than knowledge does not diminish the value of knowledge, it increases it. A truth grasped in a finite window of cosmic time, from a single vantage point in an expanding universe, is precious precisely because it is contingent. It did not have to be discovered. We did not have to exist. And, quote, the window of time in which the evidence was visible did not have to coincide with the brief period in which a species capable of understanding it happened to evolve. The alignment of these circumstances, a universe young enough to show its history, a planet stable enough to support complex life, a species curious enough to look up and wonder, is not guaranteed. It may be rare, it may be unique, we do not know. What we know is that we are here, now, in a universe that is still revealing its secrets. The cosmic microwave background is still detectable. The distant galaxies are still visible. The evidence of the Big Bang, the expansion, the acceleration, the dark energy, the cosmic horizons, all of it is still written in the sky for those with the instruments and the patience to read it. We are living in the era of cosmological discovery. We are the civilization that can still see the evidence. We are also the civilization that has begun to understand time in a cosmic sense. We know that the universe had a beginning, 13.8 billion years ago. We know that it has been expanding ever since. We know that the expansion is accelerating and will continue to accelerate. We know that the future is vastly longer than the past, that the universe has barely begun its existence relative to the eons that lie ahead. The era of star formation, the bright period when galaxies blaze with nuclear fusion, will last perhaps another 100 trillion years. After that, the stars will die, one by one, leaving behind white dwarfs, neutron stars, and black holes. The universe will enter a dark era, a period of inconceivable length in which the only remaining energy sources are the slow decay of protons, if protons decay at all, and the even slower evaporation of black holes through Hawking radiation. The largest black holes, the supermassive monsters at the centers of galaxies, will take roughly 10 to the 100th power years to evaporate. That number is so large that it defies comprehension. It is a Google years, a 1 followed by 100 zeros. During all of that time, the universe will continue to expand, carrying the remnants of galaxies further and further apart, each isolated in its own vast emptiness, slowly radiating away the last of its energy into the growing void. This is the thermodynamic destiny of the cosmos. Heat death, the final state in which all energy has been distributed uniformly, all temperature gradients have vanished, and no further work of any kind is possible. It is the state of maximum entropy, maximum disorder, maximum sameness, a universe of uniform cold darkness, stretching to infinity, containing nothing that could distinguish one region from another. Against this backdrop, our moment is astonishing. We exist in the brief, bright interval, when stars shine, when galaxies cluster, when complexity is possible, when minds can arise and ask questions about the nature of reality. This interval is cosmically brief, 100 trillion years of starlight in a universe that will endure for Google years or more. We are a candle flame in a cathedral of darkness, brief, fragile, and irreplaceable. In 100 billion years, our descendants, if they exist, may inhabit a single galaxy in an empty void. The evidence will be gone, the sky will be dark, the story will be lost. But we will have known it. We will have seen the full sky, measured the expansion, named the darkness, and understood, even if imperfectly, the vast architecture of the cosmos. That knowledge is our inheritance and our responsibility, because the universe is not going to wait. We began with a number, 299,792,458 meters per second, the speed of light, the fastest speed in the universe, the ultimate limit of motion, of information, of causality itself. We have followed that number through the centuries of its discovery, from Romer's patient observations of Jupiter's moons in 17th century Paris, to Fizeau's spinning-toothed wheel in the French countryside, to Michelson's rotating mirrors across the mountain baselines of California. We traced how Einstein transformed that number from a measured quantity into a cosmic constant, a pillar upon which the entire architecture of modern physics rests. We placed that number against the scale of the cosmos, the 8-minute journey from the Sun to the Earth, the 4-year crossing to Alpha Centauri, the nearest star, the 100,000-year traverse of the Milky Way, our home galaxy, the billions of years required to reach the edge of the observable universe, that vast sphere, 93 billion light-years in diameter, containing 2 trillion galaxies and 200 sextillion stars. We built analogies to comprehend these distances, grains of sand, dinner plates, driving speeds and walking paces, and at every scale, the same conclusion emerged. The number is not enough. The universe is expanding. It has been expanding since the first fraction of a second after the Big Bang, 13.8 billion years ago. And for the past several billion years, that expansion has been accelerating, driven by a mysterious force we call dark energy, a force that constitutes 68% of all the energy in the cosmos, and that we cannot identify, cannot explain, and cannot control. The expansion carries galaxies apart at speeds proportional to their distance. Beyond a certain radius, the cosmic event horizon, the recession speed exceeds the speed of light. Space beyond that boundary is expanding faster than photons can cross it. Light emitted in those regions will never reach us, not in any amount of time, not with any instrument, never. Light speed is the fastest thing in nature, and nature has built a cosmos that is faster. We explored the attempts to overcome this limit. The Alcubierre warp drive, an elegant solution to Einstein's equations that contracts space ahead and expands it behind, surfing a bubble of warped spacetime at superluminal velocity. But it requires exotic matter with negative energy density, matter that may not exist and certainly cannot be produced. Wormholes, tunnels through spacetime that could connect distant points, shortcuts that bypass the expanding space rather than crossing it. But they too require exotic matter, and we have no way to create, stabilize, or navigate them. Tachyons, hypothetical faster-than-light particles, trapped above the speed of light as we are trapped below it. But tachyons violate causality, have never been observed, and almost certainly do not exist in the form needed. Quantum entanglement, the spooky instantaneous correlation between distant particles. Real, verified, and utterly useless for communication, a correlation channel rather than a communication channel. And the manipulation of space itself, the theoretical possibility of suppressing the expansion locally. Dangerous beyond measure, potentially triggering a vacuum decay that could rewrite the laws of physics across an expanding sphere of annihilation. Each approach is brilliant. Each reveals deep truths about the architecture of reality, and each runs into obstacles that appear fundamental, not engineering challenges that might be solved with more time, but physical limits that are woven into the fabric of the cosmos. We uncovered the deeper truth, that the barrier is not merely a barrier to travel, but a barrier to knowledge. The cosmic event horizon limits not just where we can go, but what we can know. It defines the boundary of our causal universe, the edge beyond which no information, no influence, no signal of any kind can reach us. The observable universe is a shrinking island of knowability in an infinite sea of expanding darkness. Every second, more of the cosmos slips beyond observation, and in the far future, all evidence of the Big Bang itself, of the expansion, of the existence of other galaxies, will be erased from the sky. We reflected on what this means for humanity, for a species defined by the drive to explore, to push beyond every horizon. The existence of an absolute horizon is a profound reckoning. We can explore within our bubble, we can probe its depths and catalogue its wonders, but we cannot escape it, we cannot see past it, we cannot know what lies beyond. And yet, the very fact that we know this, that we have deduced the existence of the horizon, calculated its distance, understood its nature, and grasped its implications, is itself a remarkable achievement. We are small creatures on a small planet, orbiting an ordinary star, in the suburbs of a spiral galaxy, inside a local group of a few dozen galaxies, within a supercluster of thousands, within an observable universe of trillions. We have existed for perhaps 300,000 years. The universe has existed for 13.8 billion. Our entire civilization, from the first stone tools to the latest space telescope, occupies a sliver of cosmic time so thin that it barely registers on any chart of the universe's history. And from that sliver, from that speck, from that infinitesimal vantage point, we have looked out and understood the shape of the whole. Not all of the details, not all of the mechanisms, not all of the answers, but the shape, the outline, the grand architecture of an expanding cosmos with horizons and limits and dark energy and a speed of light that governs everything but cannot reach everything. We have understood that the universe is vast beyond imagining, stretching tens of billions of light years across, containing structures so large that light needs millions of years to cross them, emptiness so deep that millions of light years pass between one galaxy and the next. We have understood that the expansion is real, that it is accelerating, that it is carrying the cosmos beyond the reach of its own speed limit. We have understood that we live in a privileged window of cosmic time, an era when the evidence is still visible, when the story can still be reconstructed, when the clues have not yet been erased. We have understood that the universe may be infinite, or at least vastly larger than the part we can see, that what we call the observable universe, this sphere of 93 billion light-years, is perhaps a grain of sand in a desert that stretches beyond all measurement, that there may be other minds, other civilizations, other versions of this same conversation happening right now, in bubbles of light we will never detect, separated from us by expanding voids we will never cross. We have grappled with the approaches that physics has offered, the warp drive and its demand for exotic matter, the wormhole and its requirement for physics we do not possess, the tachyon and its violation of causality, the entanglement and its refusal to carry messages, the vacuum manipulation and its risk of annihilation, each brilliant, each insufficient, each a testament to the creativity of the human mind and the stubbornness of the universe. And we have understood this final, quiet, devastating truth: the speed of light, 299,792,458 meters per second, the swiftest thing in all of nature, the absolute ceiling of causality, the ultimate speed at which reality can communicate with itself, is not fast enough. It is not fast enough to cross the observable universe. It is not fast enough to outrun the expansion. It is not fast enough to carry a message from one side of the cosmos to the other. It is not fast enough to preserve the connection between distant galaxies as the universe stretches and thins and darkens. The universe is faster than light. Space grows without limit, and we are here, in the middle of it, watching it happen, understanding it, naming it, measuring it, and knowing that we can do nothing to stop it. The universe is vast beyond imagining, light is fast beyond reckoning, and the universe is faster still.